Section 2.5 is really short and sweet. It is about transformations of functions. When you took Algebra 2, you did transformations of functions every time you learned about a new function. So your teachers presented absolute values to you, you transformed the graph, you solved the equations. They did the same thing with polynomials, with quadratics, with rational functions, all the different types of functions. So we're going to spend one day reviewing all those types of transformations because they're literally the same every single time. In fact, I think I might make it easier because instead of thinking about how an entire graph might move across the screen, we're going to look at individual points. Because making individual points move on your screen makes the whole graph move, and I think it's a lot easier. But before we really get started with that, we need to look at the common graphs of functions, or graphs of common functions, so that you can recognize what kind of function we're dealing with. This little, I copy-pasted this, right? It has a whole bunch of information, but what I really want us to focus on today is the shapes of the functions. So if we're describing the shape of this constant function, what would you call it? How would you describe the shape?
A line.
Give me more descriptive than a line, because this one's also a line.
Constant. Oh, constant, zero.
Yes. Maybe like a flat line?
Flat line.
Flat line. Okay, cool. So a constant function is a flat line. It's a horizontal line. All of those things. We recognize it. This one, it says on your notes that it's called the identity function, which is true, but more likely you've called this the linear function for your entire life. We're going to call it that as well. It is the identity function when it's the parent function because it returns the exact same number you put in, which is why it's called identity. But this is a linear function. It has, again, all the attributes down underneath it. I'm more worried about the shapes of the functions today. This one, a bunch of us forgot at the door. What's it called?
Absolute value.
Absolute value. It looks like a V for value. Absolute value. It returns the distance from 0. So if you look at this function, how far away from 0 am I when I'm at -2? 2 steps. So that's why it is an output of 2. Okay, so it's always essentially going to be positive outputs, or at least returning, until you transform it, returning the distance from 0 for the inside parts of that function. And then we have this guy. Do we know this one's name? The one on the screen? Quadratic. A standard quadratic. It's the shape of a parabola, but that's called a quadratic function. The next ones are ones you're probably not as familiar with. This is called the square root function. The square root function, we know how to take the square root, but if you notice, the square root function kind of looks like a quadratic on its side and chopped in half, which is exactly kind of what it is. It's the bounded or the restricted domain for a square root function so that it is still a function. One thing I want you to know is that it's really hard to type a square root if an online program does not have a math keyboard, and a lot of them do not. So if you see SQRT and then some stuff inside of a parentheses, that's saying square root that stuff. This is also how you get a square root to show up on Desmos, is SQRT. It will automatically change into a square root. Most of my programs I use have math type, but some of them do not, including what we're going to use today for our activity. This next one is called a cubic function. Do we recognize that one a little bit?
Yes.
Here's one we probably don't. This one's called a cube root function. It is the inverse of a cubic function, cube root. It kind of looks like a square root with an extra tail on it. So what I need us to do with these general functions here is just be able to recognize and name them so that you know the type of function that we're using. Also, this is the parent function for each of them in the little speech bubble pointing at each of the functions so that you know what you're transforming each time. Now, this next little box down here is going to make 0 sense until we start going over the transformations, but it's really important that we know the order or sequences that we should do transformations in. I would follow this color code if I was you. The very first thing you should always do first is any horizontal shifting. So if we're going to take any of the input values and move them from left to right, we need to do that first before we start dealing with the outputs. After we do horizontal shifting, we're going to want to make sure we do the horizontal stretching and then the vertical stretching. Now it says stretching or shrinking because it just depends on what number you're multiplying here, but you are going to want to do all of the inside stuff first before you start dealing with the outside stuff. After we stretch and shrink our graph, we will reflect it. Reflecting is like flipping across an axis, changing the signs. And then lastly, we're going to be doing our vertical shifting, which is moving a graph up and down instead of right to left. Again, this order doesn't feel like it matters right now because a lot of times what you're going to be asked is to just identify transformations. But if you're performing the transformation, it needs to be done in this order so that you make sure you're doing the transformations basically from the insides out. Okay, what are these transformations, you might ask? The next page has all of them in one spot, which means it's going to be a very helpful page for you when we're doing our work today. Now we are going to color code this. If you followed my color code on the front, I'm going to do the same thing. Even though it's the last transformation you do, vertical shifts is what's on our page first. Vertical shifts, which are also called translations in former classes, so vertical translations, are shifting the graph up and down. If you are adding or subtracting a number on the outside of the function, you are performing a vertical shift, moving it up for plus c and moving it down for minus c. And you can see that in our little graph here if you actually take a second to look at what it's doing. If we start with the black graph and move to the blue, we see that we are moving up or we are moving down because we either added or subtracted c from the outside of the function. Now what I want you to also write down here, because again, visually, when we're doing this, it's a lot easier to transform coordinate points as opposed to shifting curvy graphs. So what I want you to think about when it comes to vertical shifts is that we are going to add and subtract on the outputs. Add and subtract on the outputs. Now we can shift things up and down. We can also shift them left and right. So we have horizontal shifts, which we highlighted in green before. This is the first transformation you perform if there are multiple transformations on one graph. For a horizontal shift, we are no longer adding and subtracting on the outside of the function. This has now moved to the inside of the function. Here's what's weird though, is that if you see plus c, even though normally plus is a right direction, you are going to move that graph or that coordinate point to the left. And if you see minus c on the inside, even though minus is normally a left direction, you're going to move that coordinate point to the right. So again, we can see on our graph here that we go from the black graph to the blue graph. We're going to move it to the left because we see plus c inside that little speech bubble. Or we're going to move it to the right because we see minus c inside the little speech bubble. Okay. What I want us to also write down here is that for horizontal shifts, we are adding and subtracting for the inputs. So vertical shifts, we add and subtract the outputs. For horizontal shifts, we add and subtract the inputs. Up next, we have our reflections. This one is not super challenging. Reflections are, I don't even have a picture here, the ones that flip over an axis. So if we're trying to reflect something about the x-axis, so we're reflecting over the x, you're going to multiply a negative in front of the function, which changes every single term in the function. You might have to distribute something here. And if you're reflecting about the y-axis, that's going to go inside the function and reflect only the inputs. So this is very important that we remember when we're reflecting over the x-axis, you're going to flip the outputs. And when we're reflecting over the y-axis, you're going to flip the inputs. Here's something I want to bring to your attention before we start piling on too many things. You notice that I've written the words outputs on 2 of these and inputs on 2 of these. Do you notice that for the outputs, which is this one and this one, both of those transformations occur outside of the f of x function? And for both of the ones that affect the inputs, where are they in the f of x function? Inside. So in Algebra 2 and Pre-Cal, you might have learned that horizontal transformations are inside and opposite. That's still the same thing. Horizontal transformations affect the inputs because they're inside, and they go the opposite way than you think. Let's talk about stretching and shrinking. So our next 2 transformations, which are dilations of the function. If we vertically stretch and shrink something, that is our pink color, just FYI. Vertically stretching and shrinking something is going to take the outputs and it's going to multiply them or divide them, which is multiplying by fraction, and stretch and or shrink our graph. So this one is kind of confusing. Let's make sure we highlight the right things. If the number we are multiplying by is bigger than 1, what we would call a Dolly Parton fraction, okay, bigger on top, then that function is going to be vertically stretched, taking the function further away from the x-axis. So you're taking the outputs and you're multiplying them by a number that makes them bigger. If the number you're multiplying by is between 0 and 1, which we would call a J-Lo fraction, that function is vertically shrunk, meaning we're going to get closer to the x-axis because we're shrinking or making the outputs smaller. So vertical stretching and shrinking, since it's on the outside, it's in front of the function, which I guess I didn't highlight that. Let's highlight that too. Look at where C is. In both options, it's multiplied in front of the function. Since it's on the outside, it deals with the outputs. So you are going to multiply the outputs. I didn't even put divide on there because multiplying by a small fraction is dividing. So we're just going to consider it multiplying, and it matters what kind of number you're multiplying by. Now, in the same way, if we take that number that we are multiplying by, and instead of having it on the outside, we take that number and put it on the inside, we are performing a horizontal stretch or shrink. So notice that the C this time has snuck in front of the X inside the parentheses. Inside definitely affects the inputs. This is the one that I always have to slow down on because I always, as a student, messed up what was actually happening here. If your number is a large number, aka bigger than 1, you are not stretching the graph horizontally. You are actually shrinking the graph horizontally because you are dividing the number by C. So you are multiplying by its reciprocal, dividing by C. If the number is between 0 and 1 that you are multiplying in front of X, that is going to be our horizontal stretch, which is going to make the graph seem longer, for lack of a better word, because you are dividing each of its x coordinates by that number C. But remember, dividing each coordinate by C is mathematically equivalent to multiplying each x coordinate by 1 over C. So you're multiplying by the reciprocal. That's what dividing is. So here's the deal. Transformations don't make a lot of sense until you actually perform them. And I want us to practice making sure that we are performing these multiplications or divisions, multiplying either the correct inputs or the outputs, depending on what the transformation is. And I want us to focus mainly on inputs and outputs. Not about the functions themselves, but about inputs and outputs, because the function will follow the inputs and the outputs.